Are there any questions? Okay, good morning. I just want to check if there are any questions on what we discussed in the last class. Any questions about the carry look ahead circuits? Okay. Yeah, because we are going to use that carry look ahead adder in the design of the multiplier circuit later, right? So it's very important that you understand that. Okay. Okay, if there are no questions, we'll get started. So towards the end of last class, we started the discussion on the design of the circuit for multiplication of integers. First, we'll look at the circuit for the multiplication of unsigned integers. As I was telling, we need different circuits for multiplication of unsigned integers and multiplication of signed integers, because the way the operations are to be carried out are going to be different. That's what we'll be seeing. And I also mentioned that any processor's instruction set will include arithmetic instructions for the integers and the floating point operands. So there will be different add instructions for the integers and different add instructions for the floating point representations of real values. And interestingly, even among the integers, the instructions will be different for multiplication of unsigned integers and multiplication of the signed integers. The reason is that the circuit that needs to be used to compute the product is going to be different, because the way the operations are to be carried out on the bit representations of the operands are completely different for the unsigned integers and the signed integers. So that's what we should keep in mind. And first we'll discuss it for the unsigned integers, then we'll do it for the signed integers. So typically, the method that we'll be using for the first circuit that we'll be designing is similar to the paper pencil method, right? We normally use for multiplication of numbers in the decimal system, right? Where given a multiplier operand and the multiplicand operand, we compute the product of the multiplicand operand with every digit in the multiplier operand, and that's what is referred to as the partial product, right? And it has to be put in the appropriate position, right? So typically it involves multiplication by powers of 10, and here we don't do that multiplication explicitly. We do the spatial shifting of the product of the multiplicand with the particular digit of the multiplier, and then realize the partial product. So basically, for every digit in the multiplier operand, there will be one partial product, and we need to add these partial products to get the final product. And we'll use exactly the same method in the case of the integers that are represented in the binary form. And first, we'll look at it for the unsigned integers. So typically, if let's say I have 4-bit representation for the operands x and y, and then I want to generate the product z, right? So similar to what we do in the decimal number multiplication, right? We take the multiplier operand, that's y, and multiplicand operand x, and then we multiply x with every bit of y. And because this bit of y can take either value of 0 or 1, right? We can realize the product of x with the bit of y in terms of the logical product, right? That's using the AND gate, right? That's why the partial product will be generated by the multiplicand operand x and some bit yi. And again, we need to perform the multiplication by power of 2, right? Depending on which bit is being involved in the generation of the partial product, right? And again, we don't do this multiplication explicitly. We've seen earlier when we discussed the representation of numbers, right? Whenever I want to perform multiplication by the power of 2, what all we need to do is shift the bit sequence of the entity to the left by 1 bit and then bring in 0 in the least significant bit position, right? And so for this example, where x is 1010 and y is 0110, right? What is shown in the black color are actually the partial products. But strictly speaking, this partial products will be of 8 bits in length, right? Because the final product will be 8 bits in length, right? So each partial product actually is 8 bits, but in the case of the unsigned integers, all these extra bits that we have here are all zeros, right? Because we are dealing with the unsigned integers, right? And typically we don't have to process these trailing zeros which are coming into the least significant bit positions, right? And we'll kind of ignore them. And in the case of the unsigned integers, the zeros in these more significant bits positions, right, will also need to be can also be ignored, right? That's what we'll be doing when we design the circuit, but we cannot do the same thing for the signed integers. So we'll come back to that later. So finally, when we add these four partial products here, we'll get the product, and we see that the product can take a values, right, which will go into 8 bits, right? And typically, many of the processors or most of all the processors cannot allow the product of the two operands to go beyond n bits, where the operands are also n bits. So we need to detect the overflow condition here. What is the overflow condition here? If the product cannot be represented within n bits, right, then we need to generate the overflow bit. Okay. So again, when we design the circuit, we'll discuss about how to generate this overflow bit in the case of the multiplication operation. So what we have seen here is for 4-bit case. Now let us generalize it for an n-bit case, right? So typically what we want to do is we have the representation of x and y, and because they are unsigned integers, earlier we've seen that the value of x can be given as summation xi to power I equal to from 0 to n minus 1. Please note that this is only for the unsigned integers, and we have seen a different kind of an expression for the signed integers when they are represented in the 2's complement form. So that's where the difference will come in the circuit for the signed integers. So for the unsigned integers, we have these expressions for x and y. Now, if I want to compute the product of x and y, right, I can substitute the expression for y here, right, and then we can bring this x inside this summation, right? We'll get summation x, yi, and 2 power I, and whatever is there in this summation is what is referred to as the partial product. Right? And that's what we generate. And then we sum up all these partial products for all the bits in the operands, right? So that's why it's a summation PPI, I equal to 0 to n minus 1, where PPI is x, yi, 2 power I. Okay. So this product of x and yi will be represented by performing the AND operation of every bit of x with respect to yi. And this multiplication by 2 power I will not be done using any multiplier circuit, right? We perform spatial shifting and then bring in zeros into the least significant bits, like what we have illustrated there. Okay. So what we are going to see now is a circuit that can realize these operations. So what is it required in order to realize these operations? I need to generate the partial products, which involves, right, performing the AND operation on bits of x with particular bit yi, and then of course spatially shifting. And once we get these partial products, right, then we need to add these partial products, and we'll be using the full adder based circuits, right, to perform this operation. So when we just translate this operation into a circuit, this will be referred to as the combinational array multiplier circuit, because the whole multiplication operation is being realized using only the combinational circuit elements. That's basically the logic gates. So I have already drawn the circuit diagram here. I want you to look at this diagram and then understand what is being done in this circuit. Okay. So we take the pair of partial products at a time, right? And then perform the addition operation. We start with the first two partial products, PP0 and PP1. What is PP0? It is the product of x with respect to y, right? And then of course 2 power 0, right? So what we have here is every bit of x being ANDed with y0. So we have x0, y0, x1, y0, x2, y0, and x3, y0, right? And it's multiplied by 2 power 0, so there is no shifting, okay? So that will give me the partial product 0. Then what is the partial product 1? X multiplied by y1, 2 power 1, right? What is x multiplied by y1? x0, y1, x1, y1, x2, y1, and x3, y1. And that has to be shifted by 1 bit position, right? Because we need to multiply by 2 power 1, right? So that's what we are doing, right? You can see that the PP1 has these bits being positioned with respect to the bits of PP0 by shifting it 1 bit to the left. So effectively, we can put 0 here, right? But that's not necessary because there's no need to add 0 to this x0, y0. So we are not going to perform that addition explicitly. Okay. So now we have these two partial products that need to be added. So we use the simple full adder based ripple carry adder, right? So the first part here is nothing but a simple ripple carry adder, which takes these two operands as the inputs and then generate the sum bits and the carry bits, right? I want to think about whether this can be replaced by a carry lookup adder, whether that will help or not, right? We'll come back to that later. Okay. So what is we get as the output of this first full adder circuits in the top row here? We get the sum bits corresponding to the sum of the PP0 and PP1. What is to be done next? To that sum, we need to add PP2, right? So that's exactly what we are doing, right? So we have generated PP2 here, which is x y2 2 power 2. So xy2 is generated by this x0 y2, x1 y2, x2 y2, and x3 y2, and then it's shifted by 2 bits, right? So we have effectively zeros here in the listening bit positions, right? And once you have this partial product, that needs to be added to the sum bits of the first two partial products in the appropriate positions, right? So that's where we are taking this second full adder output and then adding that to the x0, y0, right? And we do that for the rest of the bits. Okay. So again, we have a ripple carry adder here, which takes this partial product 2 and the sum of the PP0 and PP1 as the inputs and then generates the next sum, right? And to that sum, we have to finally add the x, y3, 2 power 3, right? So that's what you can see here for the final set of full adder circuits, right? We have x0, y3, x1, y3, x2, y3, x3, y3, and then we are shifting it by 3 bits, right? And then that partial product is added to the sum of the first 3 partial products, right? So that we get the final product. So the final product is coming out of the x0, y0. There's nothing that's being added here. The first full adder circuit in the row 1, right? Then the first full adder circuit in the row 2. Then the outputs of the full adder circuits in the final row here. So even the carry output of the final full adder stage in the last row here will also be taken, and then all these bits will be the bits in the final sum. So here these are the product bits. Okay. So as you can see here, what we are doing is nothing but translation of the operations that we have given in the mathematical form, right, into the circuit by performing those necessary operations using the AND gates and the full adder circuits. Okay. Are there any questions about this? Yeah. Okay. Now I'm going to ask you to do the timing analysis of this circuit. Okay. I'm not sure whether you had time to draw the circuit on your paper. Okay. Otherwise, please do it now. And then tell me how much time it will take to generate this product bits after all the operand bits are available. So if the operands are available at time t equal to 0, you need to tell me at what time all these product bits P0, P1, so on, P7 will be available. For this analysis to be done, you need to draw the diagram on your sheet of paper, right, in your notes. Then I suggest that you just mark the timings for each of the entities when it's generated. Okay, you just need to follow the flow of the data in the circuit, right, and then mark the time at which the different entities in the circuit will be available. That will help you to come up with the time taken to generate the output. Okay, when can all these product bits x multiplied by yi be available? It requires only one AND gate for each of those bits, pairs of bits, right? So all this x j y I will be available after 1 tau, right? Okay, I'm not marking it for all the bits. I mean, you can mark them there, right? Okay. Now, can you tell me when the outputs of the full adder circuit in the first row be available? So if you take the first full adder that is in the rightmost position, right, that takes x1 y0 and x0 y1 as input, and both these input bits are available at 1 tau, right? And this full adder circuit will be implemented using the standard method of two-level logic gate circuit, right? So this will be available at 3 tau, right? And this also will be available at 3 tau, right? So the P1 will be available at 3 tau. When will be the next full adder circuit output be available in the first row? Because this full adder circuit is waiting for this carry to come from the previous full adder, right? Only after that's available, it can generate the carry and the sum bits for that full adder, right? So this will be available now at 5 tau, and this also will be available at 5 tau. Now you can complete for the first row of full adders. Yeah. Then you can see what time the outputs of the full adders in the second row will be available. So if you take this first full adder in the second row, it gets one input at 1 tau, but the other input is coming only at 5 tau because it has to come from the sum bit of the first two partial products, right? So only after this input is available, it will take 2 tau for the full adder to generate the output, right? So this will be available at 7 tau. So this also will be available at 7 tau, right? So now let's mark the time at which the other outputs are available. Now you can see that this third full adder here, right, is getting both the inputs, that's carry input, and also these input from the previous level of the full adders at 9 tau, right? So the outputs will be available at 11 tau, right? And this will be available at 13 tau. Okay, so now you can complete the process, right? For the first full adder in the last row here, the inputs are available at 9 tau, right? So this will be available at 11 tau, right? This will be available at 13 tau. Okay, so we see that the product bits, all the product bits will be available at 17 tau. Okay, this is for multiplication of two 4-bit numbers, unsigned numbers. Yeah. Now the next question that I'm going to ask is, can we come up with the expression for an n-bit multiplier which is built using this method? So what are the operations that we are doing for 4 bits can be generalized for n bits. Circuit will be similar, right? And each row of full adders will have n full adders. I just want to give you the clue that the number of rows of full adders is, what is the number of rows of full adders here? It is 3, right? And for an n-bit adder, it will be n minus 1. So what you need to note is that there are n minus 1 rows of full adders or n minus 1 levels of full adders, and in each level there are n full adders, right? And you have to make a note that the outputs that are coming to each of the full adders in the second row and the third row, right, are coming at the same time. That's, you can, if you take the second full adder in the second row here, right, the carry input is coming at 7 tau, and the sum bit of the previous level, right, is also coming at 7 tau, right? So I just want to make use of this observation in order to come up with an expression for the delay of this multiplier circuit for an n-bit case. I'll just give you a couple of minutes to think about it and then see whether you can come up with the expression for that. I want you to give me an expression in terms of n, and of course there will be some constant values. Okay, any answers? N into n plus 1. n square is too high. Think about it. It's not n square plus 1. You have to work it out. You can't guess. You have to analyze the circuit and then look at the flow of the data and the times at which the different outputs are available, and then generalize that. I know it's a little tough one, but I want to see whether anybody can crack it. If not correct answer, at least close to the correct answer. (6n minus 7). Very good. That is the correct answer. I hope you can tell how it is arrived at. Yeah, Satvik.
Sir, good morning, sir.
Good one.
So, like, what I did was, there is a 9 tau here, right? I mean, the first full adder, the first stack of it, the output is a 9 tau.
Right.
So, which is 2n plus 1, right?
2n plus 1. Okay.
Okay. And like, when we go to the next stack of it, the carry output of the next stack is available at 13 tau.
Yeah.
Which is 4 more than 9.
Right.
And the next one is a 17, which is 4 more than 13.
Yeah.
So that happens n minus 2 times. So 2n plus 1 plus 4 into n minus 2.
Very good. Yeah, that is the correct analysis. Good, very good. Yeah, I hope people understood that. But anyway, let me just mark it here. Yeah. So basically, we see that there are n minus 1 levels of full adders, right? And in every level, right, there are 4 full adders. That's the main key thing. Okay. So how much time it will take to generate the partial products? I mean, not the partial products. The x multiplied by yi, right? It will take only 1 tau. Okay. Now, after this x, y bits are available, right? Now, let's see what is happening here. So, if you look at the flow of the data here, right? The output of this first full adder in the first row is going into the first full adder in the second row, right? So, there is a data that's coming from here, right? Which will, okay, I think let me use a different color. Right? So, we see that the carry output of the first full adder here, right, will influence the output of the next full adder, right? So that will go into the full adder stage in the first position in the next level, right? So what is the delay that's involved here for the effect of this carry to come as input to the next level full adder, right? It's 2 tau, right? And again from here to here, right, it's 2 tau. Now, in a general n-bit adder, how many such levels will be there before the final full adder stage, right? Now, in this case, there are 2. Now, the relation to the n is it's 4 minus 2, and in general, for any n-bit multiplier, right, there will be n minus 2 levels. So, the first levels of full adders before the final level of full adder will be n minus 2, right? So for the effect of the carry to go from one level to the next level, it takes 2 tau, right? So it will be 2 into n minus, sorry, 1 minute. Yeah, it's n minus 2 levels, right? And you can see that this full adder circuit's output to go to the next level full adder's input, right? It's 2 tau, right? And from here to here, I mean, I should mark here, right? It's 4 tau. Actually, if you take here, right, the effect of this input to come on to the next level's input, right? It's 4 tau, right? Again, it's 4 tau and so on, right? So we have n minus 2 stages, and the effect of the input to one stage to go to the next stage is 4 tau, right? And it's 4 into n minus 2, right? And if you look at the final full adder stage here, right? This is a simple ripple carry adder, right? And we know that the delay of the ripple carry adder is 2n, right? So the total delay is 1 plus 4 multiplied by n minus 2 plus 2n, right? And that uses an expression in terms of n as 6n minus 7. You can verify that for n equal to 4, right? It is 24 minus 7, right? That is 70 tau, right? So this is how one has to do the timing analysis of the given circuit. We need to look at the structure of circuit and how the data flows in the circuit, right? And then we need to compute the time it takes, right? And we try to come up with a generalized expression in terms of n. Now the next question is, what is this 6n minus 7 for different n values? right? Of course, 4 we are not really interested in. We are interested in starting with the byte size operand, right? So what will this be? You can verify. It is 41 tau, right? If it is n equals 16, right, it is 89 tau, right? And 85, right? And in the current 64-bit process, we'll be having 64-bit operands, right? So, yeah, whatever it is, what is that? 392 minus 7. Is that fine? Sorry. 384, right, minus 7. So that's 370. So now we see that to perform multiplication operation, it takes 89 tau for 16-bit operand, that is the unsigned short integer, right? If it is a normal integer 32-bit operand, it takes close to 200 tau, right? And if it's a 64-bit operation, it takes close to 400 tau. And if tau is even 10 picoseconds, right, it requires close to 4 nanoseconds, right? Which means that it's a 4 clock cycles minimum, right? If it's 1 gigahertz clock, right? So obviously, this is not going to be acceptable, right? So we have to see how to improve upon that. Okay, so we'll come back to that later. Before we go into the design of similar circuit for the signed integers, I want you to tell me how we can detect the overflow condition here. What is the overflow condition here? Whenever the product is not going to fit into n bits, then it has to detect it as the overflow, right? If it's a 4-bit operands, right? If the product cannot fit into 4 bits, right, then it will be overflow. Actually, the example that we have seen is a overflow case because the result that we are getting, right, by multiplying 10 and 6 is actually 60. 60 is way outside the range of the 4-bit numbers because for unsigned integers, we have seen that the range of values is 0 to 2 power n minus 1. So in this case, it's 0 to 15, right? So only if the product of these two 4-bit numbers is less than or equal to 15, then there is no overflow. Whenever it exceeds 15, right, it will be a overflow. So how do we detect the overflow condition in this 4-bit case? I have given the clue, right? If the product exceeds value of 15, that is if it's 16 or greater, right, then it will be a overflow. So if I call this as P bits, P7 to P0, right? What is the overflow condition in this case? Any answer? It's a simple expression. I given the clue that the product will be greater than or equal to 16 in this case. Okay, let me give you another clue. What will happen to the bits P5 to P7 or P4 to P7 if the product is greater than 16? What will happen to these 4 bits here? If the product is less than or equal to 15, what will be these 4 bits? If the product is less than or equal to 15, only these bits will have this least limit 4 bits will have ones, right? And all the higher order bits will be 0. And when there is an overflow, when the product exceeds the value of 15, right? What will happen to one of these or one or more of these bits, P5 to P4 to P7? At least one of them will be equal to 1, right? So we can look for that condition. P4 or P5 or P6 or P7, if any one of these bits is 1, if even one of these bits is 1, right, then there will be a overflow. Only when all these bits are 0, right, then there is a case of no overflow where the product is fitting into 4 bits, right? So it's a very simple expression that we need to implement, right? An OR operation on the higher order 4 bits, and in general for n bits, right, the overflow will be the higher order n bits, that is sorry. Because the product will fit into the first n bits, that is from P0 to Pn minus 1, right? If it is fitting into those bits, then all these higher order bits will be 0. And only when there is overflow, right, at least one of these bits will be 1, right? And that indicates that there is a overflow condition. Basically, the product that's coming out as a product of the two given numbers cannot fit into the n-bit entity, right? So that needs to be detected, and that's what is done by setting this overflow bit to 1. Okay, yeah. Any questions about this? Okay, good. Now we'll move on to design the circuit for multiplication of the signed integers, where signed integers are in the 2's complement form, because that's what we said, that's used as a standard in all the systems. So what is the product that we are just generating? Z, which is the product of X and Y. Now what is X and Y here? Again, we have n-bit representation, right? So what is the value of X in terms of the bits of X, right? If you go back and refer to your notes, you can verify that the value of X is given by minus 2 power n minus 1 xn minus 1 plus summation xi 2 power I equal to 0 to n minus 2, and we'll have similar expression for y. Okay. So what is it we're going to do now? In order to generate this x multiplied y, if I substitute the expression for x here, sorry, expression for y, right, it will be, sorry, right? So I'm just rewriting this now. I'm sorry, this should be y. Right? Okay. Can I write this one as minus x yn minus 1 2 power n minus 1? Okay. I'm just putting this 2 power n minus 1 towards the end, so that we get some uniform type of entities. Okay. What is this entity here? It is the partial product, right, corresponding to ith bit of the y operand, right? And how many such partial products we are going to have here in the summation? From I equal to 0 to n minus 2. Right? But what is the final partial product? Right? It's a pp n minus 1. And please note that this pp n minus 1 is different from the ppi. In what way it's different? It's x y n minus 1, 2 power n minus 1. For that part, it's same as the any of the ppi, right? But we have the minus sign here, right? And basically what it tells is that we have to compute this entity x y n minus 1, 2 power n minus 1, and then take the negative of that entity, right, in order to get the pp n minus 1. Then only we'll get the correct value, right? Yeah. Now, x can be positive or negative, right? Y also can be positive or negative, right? So the entity that we get here, that x y n minus 1, 2 power n minus 1, again can be positive or negative, right? And then we have to perform the negative of computation of negative of that value, right? So how do we compute the negative of any value when the given entity is in the 2's complement form? We have to simply perform the 2's complement operation, right? So basically what it tells is that after I get this x y n minus 1, 2 power n minus 1, we have to perform a 2's complement operation on that, right? And that resultant entity has to be added to the sum of the all the previous partial products. Okay, so let's take again a simple example, right? Let's say I have minus 3 and 2, right? If n equal to 4, right? What is minus 3? I mean, if you don't remember the 2's complement operation, right? This is plus 3, and we perform the 2's complement operation on that. Again, we can use the trick, right? That is, retain the first one, right? And then complement all the other ones, right? And here it's 0, 0, 1, 0, right? So when we take this product of x and y, so this is x and this is y, right? So we need to perform 0, 0, 1, 0, right? So what is it involved? Actually, I'm taking a very simple case, right? So what is the first partial product here? Yeah, it is the product of x with respect to y0, that is 0 in this case, so it will happen to be 0, right? Yeah. Next, y1 is 1, right? So when I multiply that x with x, I'll get 1, 1, 0, 1, right? Actually, there will be 0 here. We can kind of ignore that, right? Then we'll get 0, 0, 0, 0 here. Sorry. Yeah. Right? And here, we should actually multiply x with the most significant bit here, that is the sign bit, right? And then we should perform the negative of that. But because this happens to be 0 here, right, the final entity will also be 0 here. We'll take the other case and then see quickly, right? Now, each of these partial products is supposed to be 8 bits, right? So let me put the extra bits here now. So this is the extra bits. Here, right? Yeah. We can make all of them as 8 bits. Doesn't matter. What about this second partial product? We have originally some 5-bit entity here, right? Now I want to make it as an 8-bit entity. So earlier we talked about if I have the 2's complement representation of any number in some number of bits, if I want to represent the same number using more number of bits, we do that by performing what is called the sign extension, right? So what we need to do is we perform the sign extension, right? And then generate the partial product using more number of bits here. So basically, what we see is that I have to take care of the extension of the sign of this partial product in order to generate the representation of that in the larger number of bits here. Here, the larger number of bits that we are referring to is the totally 8 bits to represent the partial product, right? I mean, we can take out the last column here, doesn't matter. Okay, yeah. So this is the set of partial products that we need to add, right, in order to get the final value. And in this case, it happens to be simple 1, right? So this is the final product. What is the product that we are expecting? It is -6, right? You can verify that this is nothing but the post-complement representation of this is +6, right? And from this, if you perform the post-complement operation, we get the representation of -6. So what is important to note here is that, right, whenever we generate the partial product by performing x multiplied by yi and then shifted by I number of bits to the left, right? But we need to generate the total number of bits for this partial product to be 2n, right? In this case, it is 8, right? So it fill 1 here in the higher order bits for the case where these partial products are negative. If the partial product happens to be 0, right? Then it's 0 only. And whenever the multiplying operand is positive, right? Then the partial products are going to be positive, right? In that case, the sign extension is going to be 0, right? So let's look at the other case quickly. With that, we'll close. So let's say x is +3 and y is -2, right? So it is 0, 0, 1, 1 multiplied by 1, 1, 1, 0, right? So you can quickly do that. So the next partial product here is going to be 0, 0, 1, 1. And because this product is positive, right, we need to just extend by having zeros here. So that is the sign extension that we do, right? So the next partial product is also positive, right? So to make it all 8 bits, we'll put zeros here. Okay. Yeah. What is the final partial product now? It should be minus x y3 to power n minus 1. What is y3 here? It is 1, right? So it should be minus of x to power n minus 1. What is x here? 0, 0, 1, 1, right? So 0, 0, 1, 1 that's shifted by 3 bits is what we'll have as this x to power n minus 1. And then we need to take 1. We need to take the negative of that, right? So what will be that? So we'll take the 2's complement of this 0, 0, 1, 1 and then put it accordingly, right? So that will start with the 0 here, right? And then it will be 1, 0, 1, 1. So this is minus x y3 to power 3, right? So whenever this final partial product value is going to be non-zero, right, then we have to generate the negative of that x yn minus 1 to power n minus 1, right? Now we need to add this, right? I can quickly close this. There's something wrong here. Let me just check. We should get -6 only, right?
So the third partial product, you can check.
Oh, third product, there's some mistake.
The third one.
I
have shifted it by 3 zeros, like you have multiplied it by 2 power 3.
Oh, okay, sorry. So it should be here, right? So okay, thank you. So we can just quickly add this and then see. Oh, still some mistake somewhere. Oh, this is shifted. Sorry. So it should have been 3 zeros, right? And then the 2's complement of this. Yeah, and then the sign extension. Yeah, I'm sorry for this. Okay, now we can just add and then check. Yeah. So this happens to be same as -6, right? So now we can see from this example that the kind of operations that we need to do for the signed integers is completely different from the set of operations that we do for the unsigned integers. Now we have to translate these operations into the circuit. Okay, so I'm going to stop here, and you're going to have 4 days time to come up with similar circuit as this, right? But now for the signed integers, right? So please draw similar circuit. I'm saying similar, not the same, right? It will have more full adders because you need to do the sign extension, right? And then add them, right? And in the final stage, you need to generate the negative of the xyn minus 1 or xy3 2 power 3 in this case, right? And then that has to be added to the sum of the first three partial products, right? So the circuit is going to be different from this, but similar. So please take it as an exercise, and after you draw the diagram, then you do the timing analysis and then come up with a similar expression like 6n minus 1 7 here. What is the time that's going to take for the signed integers? Okay, so I'll stop here. So please take this exercise and do it. We'll briefly discuss it in the next class on Monday. Okay, yeah. Are there any questions? I think Ujjal had asked a question about overflow. It cannot be simply Pn minus 1 because that will not detect the overflow condition always. Yeah, I mean, this we discussed. Yeah. Any other questions? Okay, if there are no questions, I think we'll stop here. We'll close this session. We'll meet on next Monday. Thank you.